Thanks, Mike. As Mike has already said, I'm going to be talking about how you can simply reduce the carbon emissions of your building by upgrading your HVAC equipment. And so I'm going to give you a brief introduction to who we are as EBM PAPS, because most of you are unlikely to have heard of us. Then going to look at why it's so important that you should consider the fans and motors in your building when you're looking to reduce your carbon emissions. I'll go into a little bit about what the technology is, but I'll try and be brief. I want to get on to talk about some specific case studies looking at HVAC equipment in your buildings. So fan coil units, air handling units, a refrigeration plant and a data centre, to give you an idea of real examples of where we've worked with people and the sort of efficiency savings that you can expect to see. So who are EBM PAPS? We are well known as a fan manufacturer. We're the world's leading fan and motor manufacturer, a German company. And we work in many markets. So we would cover anything from electronics, cooling, through industrial applications, refrigeration. But probably our largest market is for HVAC, so heating, ventilating and cooling applications. We, as well as having a large number of production facilities in Germany, we have many facilities around the world. So we are a big company and we make products anything from a 25mm diameter up to over a metre. So we cover a vast range of products. But what I want to talk to you about today is not that, it's about our working with our end customers on helping them to look at their existing applications and see how we can upgrade the fans within those to operate more efficiently. We are working, say, with end customers, but also the likes of facility managers and M&E companies to identify areas in which they can save energy. To give you an idea of some of the applications, so in HVAC it covers domestic and commercial applications. You'll see here a mechanical extract ventilation, typically for domestic applications. There are fan coil units, but it could also be an air handling unit. In refrigeration, it could be large roof-mounted chillers or condensers, or for supermarkets, refrigerated storage. And a large important market for us is IT and telecoms, for data centre cooling. Because data centres use such a large amount of energy running 24/7, there's a lot of scope for improving efficiency within those. So that just gives you some idea of the sort of areas that I'm going to look at. So why is it important to consider fans when you're trying to reduce your carbon emissions? Well, I think we all know that buildings are one of the largest emitters of carbon, CO2 emissions in the UK, and that's both domestic and commercial. I'm going to concentrate specifically on commercial applications, and if we look at, on average, the HVAC equipment in your buildings will emit around about 40% of all the emissions in a commercial building. Now, obviously, that will vary depending on the site. But that is the majority of your emissions. And within that, the fans, pumps and motors can contribute between 20 and 60% of all that energy consumed. So it's obvious that the fans and the motors are a key factor when you're trying to reduce your emissions. I don't want to spend too much time on the technology. You can come and see us later if you wanted to learn more. But just to give you a brief idea of what we're talking about in terms of energy-efficient motors, on the left-hand side there you see is a cut-through of a AC motor. And this is our typical external rotor motor. And typically they're quite inefficient because we're getting a lot of losses within the motor. There's 2 copper windings in there. You're having to induce a secondary magnetic field to get rotation. Basically, the efficient motors that we're talking about are high-voltage DC motors. So they contain a permanent magnet, replaces some of the copper windings in there. So basically you've got a high efficient motor. It's a DC motor. But what is so important about this is that it's got onboard electronics, so that the motor, it's an AC input which converts to DC on board, and within those electronics we also then incorporate all the speed control. So traditionally for an AC motor you would have added a variable speed drive, an inverter control. You don't need to do that because that's all integrated into the electronics. It's simple to control these with adding a sensor, whether that's a temperature sensor or a potentiometer. But we'll look a little bit at that later on. Some of the key benefits, well, obviously energy efficiency is the main one, but it's important to bear in mind it's not just about energy efficiency. There are additional benefits from switching to this sort of technology. We talked about the speed control. It allows a lot more flexibility within your system. These motors can connect directly to your building management system. You can control remotely or by Modbus control. You can get constant volume, and that's all within the motor. So it's just important to bear that in mind. Also, reduce noise. If you are speed controlling the fans, they're much quieter under speed control. And perhaps from your maintenance point of view, it's important to remember the cost of maintenance. Typically in large air handling units you would have forward curve blowers with belt drives. That's all done away with, so you've got reduced maintenance on these motors as well. Just looking a little bit about, you can look at this later because I'm sure you get the presentation, but that's comparing energy efficiencies. So the centre line there is looking at the energy efficiency of a typical AC motor. So you've got the efficiency up the side and the size of the motor along the bottom. You add a variable speed drive, which you typically do, and you have the red line. We're comparing the top line. So for a 1 kilowatt motor, we're comparing an efficiency normal AC of sort of 72%, and we're looking at something well over 80%. This also just explains some of the differences in peak efficiency. And again, I don't want to get into too much detail, but it's important to know that using an EC fan, the energy efficient fan, allows you to optimise in your particular application, and you won't lose efficiency as the pressures change, for instance. But I want to get on to talk about the case studies. This just looks at some of the control that you can have within the EC fan. So anything you can imagine really, whether it's a temperature sensor, a CO2 sensor, that will can be linked into the fan and it will regulate itself. So getting on to a particular case study, this is a fan coil unit which many of you will have in your buildings, and this particular one for a large telecoms company. And so they replaced their double fan unit, so you see there 2 AC fans, swapped out for identical dimension EC fans, and on paper the AC motor is looking at about 45% efficient, which is particularly low anyway, but in reality, because it's squashed into a space that's not ideal for it, it's actually operating around about 25% efficient. So you see there 137 watts. By putting in the EC fans, they're automatically 78% efficient. So you've got a massive saving there. And actually, they don't lose efficiency when they're under higher pressures. So we're looking at 66% energy saving straight away. And in this particular example of 250 units, you see there both the monetary and the carbon savings. And quite importantly is the payback period as well. Now, it depends how often you're using your fan coil units, but in this example, on a 5-day week, we're looking at a payback of about 10 months. It could be up to 2 years, but, you know, it's a reasonable payback. Another example here is for an air handling unit. So in this case, it was for BT, and we're looking at swapping out a traditional forward curve blower and swapping that for our high efficiency motor in a different design of fan as well, so a backward curved fan. And again, we're looking at an initial power consumption. This is operating at fixed speed of 5.5 kilowatts. By simply swapping to the new fan, we've halved that, so we're down to 2.1 kilowatts. In addition to that, you can have variable speed if you want to, so they have day-night settings, so there are additional savings on top of that. Now, obviously for BT, they've got a massive estate, and they're looking at a saving of £75 million. So that is obviously something that they're rolling out across all of their estates now. It's unlikely you're going to have that much in yours, but you can see the sort of percentage savings you can achieve. Another one is looking at a chiller application. In this case, it's a supermarket. I think this is Iceland. Now, normally you would have axial fans on your chillers. Iceland are actually using a backward curve fan in this case because they're reusing the heat to circulate into their office space. Similar to the last example, we replaced with our EC backward curved fan, and you can see there again an initial saving of around about 50%. But in addition to that, then they looked at changing their speed control function. And it's easier to see if we look at a graph of the performance. So on their chiller, they had 3 fans. And you'll see on that graph there, you've got a yellow, a blue, and a red line. And they represent the individual fans. So normally they would have what they call stage control. So they have one fan on all the time, then they'll bring in another and another. Now you'll see there's 3 points on that graph. Firstly, we swapped out for the EC fans, and you'll see the drop there for around about 50%. And we're still running in the same format, one fan, then another and another. But then we looked at modulating the fans. And because of the fan laws, by reducing the speed of the motor, you're massively improving the efficiency, reducing the power consumption. You see there that all those fans are running at the same time now on that other graph. You can't quite see the colours, but they are there. And they're over 70% efficiency saving. And then just to finish off, looking at some computer room cooling. So similarly, we're changing away from an existing AC fan to EC. And here, in this example, we're looking at between 58 and 78% saving. And that really depends, again, it's on controllability. So for like performance, 58% reduction. And a payback there of about 10 months again. And I think I have some pictures to just show you in this particular example. So this is just, we would go along and work with our install partners and swap out these fans. And it's a fairly straightforward, using the existing metalwork. It would take us, we could get half a day, it would take us to change that out, and it's a very clean and 78% saving this particular company's seen. And just to finish, one last similar example. This is another unit for a data centre. We were swapping out their belt-driven blowers, you can see, and actually then fitting the fans below the floor in this example. So there are many different types of installation we can look at. So just to summarise, upgrading your HVAC equipment in your building is one of the most effective ways you can reduce your carbon emissions. It's not just that, but also government legislation is driving you that way, as you must purchase now more energy efficient motors. We can look at somewhere between 30 and 80% energy saving on your existing applications. But there is more than just saving energy. Think about the whole system. If you wanted to learn a little bit more about the technology, we have got a stand here. We're over actually by the Energy Theatre 2. So if you wanted to learn more, come over and see us there. But now I'm going to hand back to Mike.